Alrighty, so tonight's talk is going to be about compilers. And the goal is just basically give a high-level overview of how a compiler works. And I'm going to be kind of skirting the topics across the top. I'm not going to go super deep into any one of them. So that way when you're done, you'll be a little bit, you might even be a little overwhelmed with all the little terms that I've given you, but you'll be able to go back to the slideshow, which I will share with you, and then you can Google deeper on each one of these issues. But at the end, you should be able to know enough that when you look at your code, you won't ever look at it the same again, because you'll look at it in sort of the way that the compiler looks at it. A little bit about who I am. I grew up here in Wichita. My name is Joshua Young, last name like Carl Jung. That's the easiest way to remember that. I grew up here. I was involved in homeschooling and BEST, the robotics competition. My dad owns a bicycle shop here. And I got involved in computer programming from a young age and have been doing it now for about 20 years total. I've got a bachelor's in computer science from UIC. I lived in Chicago for about 9 years. Got my computer science degree from there. Actual professional experience, about 10 years right now. Wide range of languages, C, C++, did 3D game programming when I was in high school, then got involved with web and was doing Flex and ActionScript and Cold Fusion and Java and the whole 9 yards. And then lately I've been doing Node.js and mostly HTML5 stuff. So, purpose of the talk, I already talked about this a little bit. I want to introduce you to the core concepts of compilers. Focus on principles and terminology rather than implementation. So I'm not going to actually open up my command line and walk through some stuff with you. I'm just going to blast it out here on the screen for you, and then you can go home and work on it yourself. And then I want to get you excited about some core computer science concepts. I know from talking to different people in the dev community here in Wichita, there's a lot of people who are self-taught. And when you're self-taught and you go online and you read Ruby articles or you read PHP articles or what have you, they don't really dive into the computer science concepts very much that are sort of the foundation of why they chose the things they did about the languages that they created. So I want to get you excited about that. Feel free to ask as many questions as you possibly can. I will be looking up. If I don't see you, please just say something. And if you feel lost, don't worry about it. I guarantee every single person in here is going to feel lost at some point during this talk, just because having taken a compilers class, having written some parsers and done some compiler stuff myself, there's going to be topics that I'm sure I've forgotten I knew, so to speak, that I might have to re-explain in order to catch you up to where we were. All right, let's go ahead and get started. Anybody have any questions, though? Any questions so far? All right, let's go way back to 1837. Anybody have any idea what happened in this year related to computers? You?
How old is Charles Babbage?
Yes, yeah, that. Okay, so this was Ada Lovelace and Charles Babbage. Basically, they worked together and came up with the concept for an analytical engine, which was never actually built at that point in time. It was all sort of designed on paper, and then it was never made a reality until much later because he couldn't get funding to build it. Ada was involved in creating the first algorithm for a machine, which is pretty cool. This machine itself contained an arithmetic logic unit, control flow, conditional branching, you know, your if-else sort of concept, actual working memory. My understanding was the original plans actually planned for 1,000 mechanical numbers with, I think it was 50 digits each or so, which is pretty crazy for a mechanical machine. And the whole thing was mechanically programmed. Obviously, you didn't have a programming language for it or whatever. This is an example of what it looked like. This is one that was built many years later to try and illustrate what he was getting at. And the whole thing was driven by programming it through punch cards. So you had these, you drop pins in, one each one being one bit, and that's how you program the whole thing. Fast forward almost exactly 100 years later, and we encounter Alan Turing. And many of you have probably already seen The Imitation Game. If you haven't, I highly recommend watching it. It's a really good sort of overview of the events in World War II that led toward the development of all the theory that we now use as the foundation for computers. Definitely worth a watch. So let's get into the meat and potatoes here. A Turing machine is an abstract machine, and I want to highlight abstract here, because if you read up on Turing machines, you're going to start to discover very quickly that all of the math and everything that's written down doesn't actually relate to anything physical at all. And they'll oftentimes use terms that almost assume that you have unlimited memory, unlimited amount of CPU power, et cetera. And then all they're talking is numbers, like how many ticks does it take to solve this problem, right, in relation to the size of the input of the problem. Another way to look at it is a mathematical model surrounding the device itself. And this is it. All it is, the whole concept behind the Turing machine is you can solve anything that you can describe with an algorithm with a tape driven by one little reader that reads one character at a time. And that little reader is driven by a program that can either go left or right to the slot, or read from the slot it's looking at. And you can solve just about anything with that. And that is the foundation of our computers today. The concept of Turing complete, you've probably heard that term before, means that a machine can solve any problem that can be solved by a Turing machine. So, repeat that again. So, Turing complete, given any computer algorithm, a Turing complete machine can be constructed as capable of simulating that algorithm's logic. So you've got, well, I'm not going to give you an example of a non-Turing complete. That would get a little too deep right now. But if you want to dig into that more later, you can. Like I talked about a little bit ago, a Turing machine assumes you have unlimited speed, unlimited memory. And they only model the computation. This is a Turing machine built out of Legos. Unfortunately, it is limited by time and space, so it can't solve anything a Turing machine technically could. But our modern computers are an implementation of a Turing machine. So, given that, all right, we've got this idea of this abstract computer that we've built in our machine, and then we've converted into something physical sitting in front of us. What is compilation traditionally? Anybody want to take a stab at sort of describing what compilation is? Go ahead, Jacob. Good, very good. A little bit more history. Grace Hopper, another woman. I think this is fascinating because we don't have enough women in the computer industry, if you ask me. Another woman was foundationally involved in coming up with the very first compiler back in 1951. I think that's fascinating. But the idea was you had this Turing machine, you had your physical CPU, and like you said, we've got machine code. Machine code, like those punch cards, drives the CPU, and then our programming language is essentially compiling, using the CPU, the actual written code into the machine code that can be run by the CPU. That's what it traditionally means. Here's a C example of this. So here we have our basic hello world in C. And if you were to take this and run your GCC on it and output you can stop GCC and spit out the assembly code. So that way, before it converts it into object code, which we convert into your executable, it would look something like this. And here we have a more, I mean, certainly doesn't look nearly as elegant, but this is just step one in the compilation process. But this whole portion here is actually considered one compiler. We're compiling C into assembly. And then at some later point, we then compile the assembly into our machine code. And just for fun, I threw in a punch card here from one of the old 1970s machines as an illustration of what, a good example of what that output sort of resembles. All right, there are 4 major steps in compilation. First one is Lexing. That's where we take, we'll get into that in a little bit. Then our parsing step is where we take its tokens and we construct an abstract syntax tree out of it. Third step is semantic analysis. This is where we do things like check to make sure that you don't use a variable before it's defined. That's not something that you would normally do during the parsing step. That's something you would need to do later. And then finally, we generate the output, which is our target language. So in the case of what I just showed you before, our target language might not actually be machine code. In some cases, it might be, well, a good example of it, we heard CoffeeScript. You might have a compiler that converts CoffeeScript into your native JavaScript, right? But that's not really machine code yet. And then you'll need another compiler inside of your Chrome browser to convert that JavaScript into your machine code that's run on your local machine. That's why I use the word traditionally when I describe what a traditional compiler does. So Jacob was correct, but there are the compiler definition has been expanded to include all these other different ways of discussing it. All right, let's jump into Lexing. I just mentioned tokens before. Does anybody have an idea what a token is in respect to compiler? No? Let's take a simple expression, something like what I have listed here. In this example, a token would be your 1, your 3, your pi, your 7. In addition, plus, times, divided by would be tokens, and your parentheses would be tokens as well. It's basically one unit that can be pulled out from the rest and separated from the rest that has its own semantic meaning. Now, when we pull these tokens off of our input, we don't necessarily always do things in the computer in the order in which we pull them off, right? So you construct a string of characters. You can't just read one character, do something, the next do and then reconstruct a completely different ordering. And this is a good example because we would want to perform 3 times pi first because it's in the parentheses, right? So this is something we have to take into account. In addition, we have operator precedence. How in the world do we manage picking which operator comes first, right? We can't just do them in order from left to right. Sometimes we might need to do right to left. And then this is an example of the solution here where we slowly break the thing down. In addition, and I threw this in here because I feel like this is one of those concepts that helps expand my mind a little bit in understanding the ways in which computer can approach these problems. Let's take a simple expression like this. How many different ways do you think you could write this exact same expression? Yeah. There's quite a few. But one of the things that most people don't normally think about is the fact that you don't even have to have the operators themselves in the right spot, so to speak. You could do something called prefix notation, where you set your operator first and then your operands after that. So here would be an example of prefix notation, where we do plus 3 minus 2x, and then this, I'll show you an example on the next screen of this actually breaking down with the stack and everything. Another example is postfix notation. So in that case, you would do the operands or the operators after you put your operands on the stack. And then our traditional notation that we're taught when we go to school in algebra is infix notation, where we list it either like above or another example like I've shown here where we do 2 minus x plus 3. And computers don't really care which one you do. They don't care at all. You can write a compiler to work any which way on these. So here's an example of our prefix, or what is sometimes called Polish notation. I don't know why it's called that, but I know some of the old HP calculators are called, you've heard of reverse Polish notation, where you enter things in backwards. So this is just an example of how this would work. The idea is that inside the machine, you have a stack. And the stack is just something you push things on the calculator. You would push the plus onto the stack. And then if you were to enter 3, it would push 3 onto the stack. Then you'd enter your minus, it push minus onto the stack. The computer at this point still sees that the plus needs at least 2 operands in order to work, right? So it's not going to do anything. It will ignore the plus for now. Then we would enter our 2 in, and push the 2 on the stack. You'd enter x in and push x on the stacks. And at this point, we've got a special case. It sees that the minus can be resolved, and we do what's called a reduce step, where we resolve 2 minus x. In this case, x equals 7. So that gets reduced to -5. And at this point, the computer goes, oh, hey, guess what? We now have our 2 operands for our plus, and we can reduce these down to -2. So at this point, we've entered our operands and our operators in a different order than you would normally expect. Now, why would this be important? Like, most of your programming languages don't involve prefix or postfix. Like, can anybody give me an idea why this concept would be important? Sort of, you're getting close, yeah. It has to do with the fact that it gets us thinking about how we structure our data in the memory of the computer when we're entering stuff in. Because in this case, we have a simple stack that we're working with. And with prefix and postfix, it's kind of nice because all we need is a stack, that's it. We don't need to worry about things like parentheses and all of that, right? Because we just enter things in linearly and the computer takes care of the rest. All right, table that concept for 1 second. We'll come back to that in a little bit. I'm going to do a quick regular expression refresher because this will come important. These two concepts will kind of come together here in a little bit. Many of you are familiar with a regular expression to parse an email right now, or an email address. You got one? I couldn't do it. I mean, because there's so many rules regarding email addresses that I don't know that I could do it. I could get close, but a regular expression is a sequence of characters that define a search pattern. So essentially, it's a very concise way to describe a particular type of thing you're looking for in a string. And here's an example for an email address. And I'll leave this up here for a second so you guys can look it over. We got our /b for our word boundaries at the beginning and the ends. The @ symbol is pretty self-explanatory. And then the other portions are just your special characters for each portion of the email. Clearly, you've got your dot here for like .com or something like that. Apparently, there's a rule that says that you can't have over 6 characters in the extension. But this is just one example of a regular expression. And we use regular expressions to grab our tokens. In a calculator, when you enter stuff in, and the calculator knows you're done entering something in because you're going to press enter or you're going to press the next like plus or minus or something like that, right? When we're parsing stuff off of a giant file, for example, there's nothing to indicate to us through user input when the end of a word has been found, right? So we have to write regular expressions to find what way the token is supposed to end so we know to move on to the next thing. All right, so we've got our regular expressions. We've got our concept of tokens. Most lexical analyzers, and there's actually really cool tools out there. One of them is called Lex. That's actually the famous one. I think it was written in the late 60s, early 70s. That's designed specifically to create rules based on regular expressions. And you create a giant list of them in order of precedence. And these can contain regular expressions or they can contain other rules. And you build these up to basically design your language. And so this is actually how something like C works. They use something like Lex to build these rules up. And I'll show you an example here. Here's some really simple ones. So I think these regular expressions are pretty straightforward, but I'll explain them anyway. So the top one here just basically says that we're looking for a character that has either 0, 1, 2, 3, etc. through 9. And we need at least one of them. That's what the plus sign means. So this would recognize any integer. Now, can anybody spot a problem with this one, though? What do you mean?
Well, it just finds all digits, so I don't know if it's the problem.
It would, yes. I mean, no, it will stop on a space though. So it'll stop on a space. So if you had 100 space 100 space 100, it would capture that 3 times. This is actually an example from the paper that I found down here, and I noticed the problem later. The problem is the numbers cannot begin with 0. Right? You couldn't have 0003, and that's not a valid. Like, what is that supposed to mean? There's no decimal point in there, right? So this is it technically is a valid number, but normally that would not work in a language. So regular expressions are tricky. It's good to like try them a million times over with a ton of different inputs. What about this second one? Why do you think they've excluded, they've got a separate portion at the beginning here rather than the second portion? What's one of the rules for naming variables? You can't start with a number, right? So this is an example of how you could define your name for an identifier, like a variable name or a function name, using the program called Lex. If you look Lex up online, you're going to find probably 20 or 30 derivatives of it. Lex is the original. It's often combined with another tool called YAC. They're often kind of put together. I think YAC stands for yet another C compiler, I think is what it's called. And then as a joke, everybody after that just calls all of the tools that are based on YAC after bovine. So it's like bison or I can't remember what the JavaScript one was called. So if you see anything named after a bovine, it's probably based off of YAC. All right, let's get into some more complicated ones. All right, so let's take our calculator example. We've got a calculator, and we need to write rules to recognize things like plus, minus, times, division, that sort of thing. Here's an example of plus and minus. I'll leave this up here for a second so you can take a look at it. This right here is actually a full description of a language, quote unquote. And this language has defines the concept, a token called a program. A program can be a program followed by an expression. There's a recursive element there, which essentially means it can be any number of expressions. Or a semicolon. Your expression here can be an integer, or it can be another expression plus an expression, or it can be another expression minus an expression. Anybody's head spinning yet? Is this making sense? Any questions or anything? All right, I'll assume it is, unless somebody raises their hand.
Dollar signs.
Dollar signs. Okay. So within Lex itself, Lex actually takes what you write here between these percent signs, and it has special rules that actually converts this into C code, which is really cool because when you run Lex against your file that looks something similar to this, you can actually see the C code it produces and see exactly what it is building that's going to run against your input. Everything within these brackets will be converted into code within a function. So you can put any C code within these brackets and do special things, which I'm not going to get into now, but when you start to study how variable names are stored, how values are stored and passed through from one portion of a program to another, being able to write custom functions is incredibly important, especially things for like caching and optimization. The $$ here indicates output. In this case, for an integer, the $1 refers to which operand within your statement. So take, for example, this expression plus expression. $1 refers to the first operand, which is the first expression. $2 would refer to the plus sign, and $3 would refer to the second expression. So what this is saying is that we're just going to add together the first and the third expression and return the value, right? So it's not too complicated. So this is an example of the type of program that would recognize an expression like this and would be able to return the result for you. One interesting aspect here is that with calculators, you are actually part of your Lexer. You're playing that role. So when you're writing a compiler, you're trying to play that part of those steps that you mentally think through when you're using something like a calculator that you are trying to automate with the machine. All right, now let's combine these two together. Okay, so we know how to parse our tokens off, right? And we know that we need to be able to process something like infix, where where our operators are in between our operands, 3 plus 2 instead of 3, 2 plus, or plus 3, 2, right? I'm just going to throw out an example of what an abstract syntax tree might look like for this 1 plus 2 minus 3. What this is saying, how many of you guys are familiar with the computer science concept of a tree? Okay, let me all quick explain it real quick. The idea of a tree is that you have a single root node, and that each node within your tree, each element within your tree, can be connected to one or more child elements, and there are no cycles, meaning that you can't have one connected to two here, or else that's no longer a tree. So you can't have, any node can only have one parent, is another way to describe that. In this example, what we do in your abstract syntax tree is we dig as deep as we can into the tree, solve the items at the deepest level, and then we move up. And then we solve there, and we move up. So we do 2, 3, minus. So we do 2 minus 3, and we put the value in that box. And then we do 1 plus and the value in that box, and then our root node would contain the result. So at this point, we don't really have any paper, so I was going to have you guys figure this one out on your own. Take a look at it for a little bit and see if you can kind of figure it out in your head. Just a second. I'll give you a minute or two. All right. So the end result is going to look something like this, where we take our 3 and our pi, because that's the first thing we need to solve, right? We're going to put those in our what's called a leaf node in the tree, meaning it has no children. Obviously, those are multiplied together. Once that has been solved, our operator precedence says, which do we do first, division or addition? Division. Division always gets performed first. So we would then take our 7 and divide that. And then we would do our 1 and our addition. So here's the abstract syntax tree for that basic expression that we just listed there. So taking that, now what we need to do is we need to start building a giant abstract syntax tree for all of our actual expressions within a language. Things like if and while and do and other things like that. This is where things start to get a little bit more complicated. Thankfully, I found this example online, which doesn't get into the nitty-gritty of some of this stuff, but kind of shows how it can work. Here we define a statement. Before we were dealing with expressions. Statements generally, there's kind of the implicit rule of a statement is that it doesn't have to return a value. So for example, if you say print hello world, it doesn't have to return anything, right? It doesn't, you couldn't do 1 plus print hello world. That doesn't make any sense, right? Because print hello world doesn't have a return value. So in most of your statements here, they're not gonna have a return value, like if statements, that sort of thing. But these are good examples of how you could write these out using Lex. And then you have the concept of a statement list, and that's a series of statements in a row, one after another. So as a good example here, you'll notice that your if statements, or your if statements don't have to end with semicolons. You could just string if statements one after another, because your statement list could be followed by another one. And then here you can see the $, the $1, $2, that sort of thing in work. But one of the core concepts here is that recursion is essential to this parsing. You have expressions being put inside of expressions, and you have statements being potentially put inside of statements. Take, for example, the while here. You've got while, you've got an expression, then you have another statement. So you could do a while inside of a while, inside of a while, inside of a while, and Lex would be able to recognize this consistently. Here's a little more information on expression versus a statement. Is the first item listed here a valid piece of code? This top one here. No. And why? What would be the reason for that? Exactly. Right. Yes. So the answer was, Jacob pointed out that the answer is that if is an example of a statement, it doesn't have a return value. And in order to pass something into a function, which is what we're trying to do here, you have to have an actual value to pass in. And that's why something like this is an invalid piece of code. What about the second one? Is this valid though? My understanding is that I don't know if there's any languages where this is invalid. I think all ternary operators, which is what this is. Is everybody familiar with what this is right here going on? Anybody unfamiliar with this? So essentially, this is the same thing as what's listed above in the if statement. The difference is when you use the question mark, which is a ternary operator, the value is returned. So in this case, when we call do something here, if A is true, 3 gets passed in to do something. If A is false, then 2 gets passed in to do something. So this is essentially the proper way to do the code above. And the reason is that a ternary operator is an expression and not a statement. So there's a return value. And then here's some examples of other statements being hooked together in valid ways, except for this one, which is also invalid because while is a statement, and you can't have a statement inside of the if definition because as we look back here, if requires an expression in between its parentheses rather than a statement. And while is defined under the statement category. So this actually brings us, and this is the final part of the talk actually. I'm surprised I made it through the whole thing. I was kind of afraid we were going to get stuck on some slides. Knowing this stuff, once you know these things, and you know how the compilers are reading this stuff, you can start to kind of perform some tricks in your code because you can put expressions where you wouldn't normally think to put them. One good example of this, and you've probably already seen this in JavaScript, is the OR expression, where you default a value. What this says is we're going to assign B equal to some value unless some value is undefined, and then we're going to make it equal to 0. Right? If some value is anything, a string, an object, or anything like that, there's actually, I'm trying to remember the term right now. The internal of the computer, when it sees an OR, what it'll do is if the left-hand side is true, it knows that it doesn't need to evaluate the right-hand side. So this is actually a trick you can use. If you have two really, really expensive functions that you need to perform, do an OR like this. Because it won't, as long as the first one returns true, it won't even bother trying to call the second one. Right? So let's say some value is a function and 0 was a function over here too. If some value returned true, it wouldn't call the right-hand side. It's rather than doing var a equals your first function, var b equals the second function, and then doing the OR, do it in line. It'll actually save you some time. Is this valid syntax? And if so, why? Anybody? Correct. On a function, you can't. But what if a function returns another function? So what ends up happening here is that this gets evaluated as a function call expression. It returns a value, as expressions do. And then that return value, if it's a function, it sees, oh, we're going to call again on the next one. And then we can call again on the next one and the next one. And then we have a ternary operator, and then we can call our yep or nope functions here. So this is actually valid. Once you understand how these expressions work, you can start to do some fancy stuff like this. What about this? Is this valid?
some functions
Right.
return a function, and then run that function, and then whatever that function returns.
Correct. Right. So assuming that your sum function's working the way it's supposed to, this would be valid code. As long as the return values are what you expect, this would actually work. You can actually use this if you have a factory function. This syntax can be used because you can return another object type or a constructor, right? And then you can call new on whatever that function returns. Here's another good example. Is there anything that says that you can't just have a block statement sitting out in the middle of nowhere? You can actually use this for scoping. And my understanding is that your Babel compiler and that sort of thing, where you've got your new let variables and things like that, when your arrow functions and whatever, they use some of this stuff internally to ensure that variable names don't collide. Because you don't need an if in front of your block statement here in order to set off a scope. So you could have two A variables here, and the second A variable inside this scope isn't going to override the outside one. This is just another example of the type of trick. Once you learn how compilers look and break apart their expressions and statements, you can do some pretty wild stuff with it.
Does that work though? In JavaScript, not in ES6. Like in your for loops, in your if statements, those are not.
I believe you
can.
can. Well, I know for sure this works in C++, and I'm 99% sure it works in JavaScript because it's the same.
Like your function is the scope, but all that those are statements and for statements. They aren't the scope. That's why
Yes, I know what you're referring to. And
let's do it instead, even though it doesn't.
So, my understanding, I would have to test this later. I was just kind of harkening back to C++ days. I know this will work there. In JavaScript, you've got a good point. Right. Yeah, and scopes are built inside the compiler in a tree fashion as well, and they always look at the most immediate scope. And then they destroy, when you step out of that scope, it destroys all the variables in the parent scope. So in this example, assuming JavaScript is built the way most of the other compilers work, it would create a new scope because we see the beginning and ending brackets here. It would create a new A variable in that scope. And then when you do console log, it would look at the current scope first, find that A variable, print it. And then as soon as you exit the block, it'll destroy that A variable. And then when you do console log, it'll look at that current scope, which gives us the original 1 value. That's the way it's supposed to work. Now, whether that actually is the way it's going to work when you run it in the browser is a different question. But that's the way almost all the compilers that we were taught work. That's how they do it. So, this is supposed to say 2 of 2. Here's another example. I've actually used this before. There's nothing that says you can't just have an expression. So let's say you want to do, instead of if some variable, then call a function. This actually works. Now, why does this work? Well, first off, what does it do?
Do something if A is true.
Yep. And if A is false?
Then it's 0.
Yes. And in this case, it'll just discard the 0 value because there's nothing being assigned to it or it's not being passed to anything, right? So internally, the compiler, I imagine, is going to be smart enough, especially with something like Chrome, to ignore the else portion and just not do anything. But this is a good example where you can have extraneous code sitting out here, and you might see someone else's code that's written to be optimized, in particular minified JavaScript, where you might see some tricks like this being performed. And what they're doing is they're basically using the trick like with the compiler to say, hey, I'm going to shorten my code, but perform the same thing I would get with an if statement. Here's another example. If any of you know what Lisp is, you'll understand the joke. Lisp is a language that was known for its heavy use of brackets and parentheses everywhere. So this is actually valid code as well. There's nothing that says that you can't have an infinite number of blocks nested deep and then put something inside of them. It doesn't look pretty, but I suppose if you want to have a signature about what your code looks like, you could double block everything. And
It's got its own sort of aesthetic.
it does have its own.
It's sort of dramatic.
It is a little dramatic. It's like, please pay attention to this one line of code. It's super important.
You can line some comments and make some fun. Yeah, right.
Yeah, you could. I believe some of the competitions where people do, what's it called? The obfuscated code competitions, they'll do tricks like this, where they want to make it look pretty or look like a picture, right? So they'll do hello world with 20,000 characters and they'll have this beautiful picture. This is one of the tricks that they might use to do that. Here's another more generic example where you can just start stringing stuff together without using block statements, because nothing says that you have to use them for ifs and whiles and that sort of thing. That one's pretty generic. But I do kind of want to point this out. If you do start to do compiler design, one of the things, I probably should have chosen a better example of this. One of the things we were taught is that the dangling else is one of the most difficult problems to solve in compiler design. What if you have a whole bunch of if statements like nested, and then you have one else? Which if statement does that else belong to? How are you supposed to know? And the rule is it always belongs to the last one. But there's actually one of the difficulties of using regular expressions and the sort of definitions that Lex uses is that it's actually incredibly hard with the basic rules that they use for the computer to figure out which one it's supposed to belong to. So I'll just throw that out there. If you run into that in your code when you're reading through like a Lex tutorial, just remember that I brought it up and that it's really difficult. And if you don't get it the first time you look at it, it's perfectly fine because we spent a whole week on it in class. So, and he told us if you don't get this, it's fine. Here's another example. This is perfectly valid code. You can multiple assign variables. You've probably seen that before. Where you, and in this case, you don't even need parentheses for anything. So in this example, it's gonna, what is it gonna do first here? It's gonna run get value, then what's it gonna do? Correct, right. Because assignment operators are always listed last. You know that statement list where we were working through the statement list? As a general rule, assignment is considered one of the last things you're supposed to do. But if is always done after that. As far as your mathematical operands and your ternary operator, it's always last. So in this case, it would evaluate get value. And in this case, this is completely redundant because if it's true, it's going to be true. Unless get value returns it. This is JavaScript, so it gets even trickier, right? Yeah, because if it returns an object, right, you might want to cast that to true, which means that this would work. But in this case, we're going to do something. But that's all I had. I just wanted to give a high-level overview of everything and throw it your way and see what you thought. So. Yeah. Yeah.
Doesn't work as expected, but if you are in strict mode and use let instead of R, then it will work.
Okay.
Yeah, that's why let was brought up because it doesn't work with
because we want to work with interact.
Okay. That's a good point. I'll go back and edit the slides then. So basically, we're going back to.
Somehow JavaScript broke that. I was wondering how
yeah.
It sounds complicated. It's like yeah.
So. That's right. It is the hoisting because all of these, if this is inside of a function, the var a is going to get hoisted. The definition of var a, which means you only have one var a defined. So in this case, console log here, the second one would return 2. So good point. Yep, exactly. So in C, C++, this would work as I described. In JavaScript, I completely screwed up because this is not going to, well, JavaScript completely screwed up.
Right.
But we're like, it'll compile, right? It does. right to the
Kills you when
2.
you run your for loops, because everybody does for I var I equals whatever. And you do it later, but that var I
But the var I
is not scoped into that for loop.
it's
wasted.
scoped for
And now
some.
you get
Yeah.
that I coming back later. And you're like, what?
Right. Right.
So,
I was use J next.
right. Because they relate
Yeah.
on the whole program. You don't expect that I to be
No. No. Not at
that
all.
pages down the same function.
Awesome. Any other questions?
So when people write like silly languages, they'll they just write a bunch of Lex rules.
When they write what?
Well, like some people do like silly languages, like
Oh, like the
yeah,
Arnold,
that kind of
whatever.
thing.
Yeah.
I think usually like each election cycle will be made based on some politician or whatnot. Yeah.
Yes.
So that's just Lex rules and stuff.
Yeah. So a lot of those, what they'll do, like if I were to do it, I mean, if it's a simple enough language, you could write the parser yourself. And I've actually, I've done this before for in a couple cases. Yeah, you could write the whole thing yourself, but I would recommend doing something like, probably if you want to write a language, here's my recommendation. Learn Lex, and then learn how to write the definitions, even if it's a simple language, and have it output C code. The reason is that if you output C code and then compile the C code, you get all the advantages of the optimizer and the C compiler. Whereas if you try to write the whole thing yourself and directly to machine code, you're going to have to deal with all the different CPUs. You're going to have to deal with optimizing for all the different CPUs, and it becomes a nightmare. And so a lot of your new languages will just go directly to C, because then it's like, all right, I'll just let you guys take care of it from here because this is too complicated.
They are writing Alexa.
They will write a Lexer, and I would highly recommend, no matter how you approach it, it just gets way too complicated. Always make sure whatever tool you're using builds an abstract syntax tree. I've seen a couple people actually at presentations, one of them was a JavaScript presentation, where he didn't understand what an abstract syntax tree was, and he tried to write his own parser for doing custom stuff, and he basically reinvented the whole concept of an abstract syntax tree without understanding there were all these tools out there that were already designed around all the math for it. And I talked to him afterwards, and I felt so bad and so good at the same time, letting him know, hey, man, you don't have to keep working on this. This has been solved like 40 years ago. So just keep that in mind. This stuff has been studied to the nth degree. So
There is a talk under Plains. It's about Arnold, the language. And that's what they talked about, those Lexers. They went through it.
Oh. I was there. I didn't go with you to that talk, I don't think.
That's what
Yeah.
it's about. It's
Oh, very
a
cool.
little less, different angle.
Right,
Than
right.
that one. This one.
Awesome. Very
That'd
good.
be a good companion topic. That have one on. First half is like the language is always jokes. And I went to a joke class, but the second explained
Right. Very cool. Any other questions? Yeah.
How about some languages that omit quite a bit of things like curly braces? So in Python, you have white space on the left side, which is significant.
Yeah, that's actually a really good point. So what you can do, yeah, so the question was, what about languages like Python where you eliminate your braces completely and instead you're basing it on white space? Well, the cool thing is there's nothing inside the Lex definition that says that you can't look for 4 spaces, right? And there's actually a special Lex instruction. If I remember correctly, seeing in the documentation, there's a special Lex instruction you can actually specify to say treat white space as significant. And then all of your definitions inside of your statements and expressions, it's actually going to look, it's going to require you to say, hey, this is arbitrary white space versus this is significant white space. So in that case, you could say, that's a really good question. I don't know how you would write that out here, but there's, I mean, a white space is just a character, right? So you can tell it to look for spaces just like you would underscores, and treat them as special.
So, like having 4 spaces would be like a bracket is basically that tons of brackets code just put white space.
Correct. I think they don't necessarily treat 4 spaces as a bracket. They treat like 4 beginning spaces, 4 indentations at the beginning. But yes, you're right. Essentially, every time you indent, that becomes significant because it's always going to reference the parent that is not indented as its parent block.
Well, in
That's a
Python,
really good
you
question.
see a colon first, and you be expecting indentation. No, further in. Anytime you saw a colon, it would be further indented than the parent was.
Okay. Well, that would be even easier to define here in the Lex rules, right? Because you can just do colon followed by. You could actually, instead of EXPR, you could have a white space definition. And then inside of your code here, you could measure the length to determine the context of its parent object, to determine how deep you were with that code and which while or which if it was referencing. Very good question.
Does the Lexer then return errors when you fail to Lex?
Yeah, so actually, unexpected end of input would be an example of a Lexer error, right? It just never even, it just stopped, like something was broken. In the 2 phases that we were talking about, Lexer versus parser, your syntax errors are almost always found in the parser stage. So that means that, okay, Lex just fine, all of our tokens, we got those taken care of. Semicolons are okay, but now we've got some other problem that's a little bit deeper. Some compilers will combine the Lexing and the parsing phase together, and I could imagine that in some cases that would improve the performance of the compiler, just because you can kill 2 birds with 1 stone cycling through the code. I would imagine that Google Chrome, when it's parsing your JavaScript, tries to do that as much as it can with its high performance characteristics, but I don't know that for sure.
What I wonder about is like IDEs. I love using IDEs that like pay attention to code. And you often find things that it's like that. If I'm typing in PyCharm, if you don't have an indent after your colon, it's going to flag it right away. If you're going along, so it's big red in front of you. It's really fast to see that.
Right.
If it's using Lexing or something.
It is.
That's not going to fly.
And that's actually a really good point because you don't even necessarily have to build a compiler to make use of this. If you've got your favorite IDE editor and a language that hasn't been supported, you can often find, for any language out there, JavaScript, there's tons of them. You can find pre-built Lexers and parsers. And I actually did this for Sublime Text because I was trying to build a JavaScript checker. And I thought about it, and I was like, wait a minute, all I need is a Lexer and parser, right? And all I need to do is once every time you save the file, run the whole thing through the Lexer and parser. If it doesn't spit out any errors, I know it's valid JavaScript. And if it does, I know there's a problem with it. It's just super simple binary, right? So I built the whole thing out, got it hooked up, and then Sublime Text has special, they tried to keep it simple by not allowing you to output any like special colors or pop-ups or anything. And so it was almost useless at that point because I couldn't actually output the results in a meaningful way on the screen. But you don't even necessarily have to know, now that you know what a parser and Lexer is, you can go find one and hook it up to your favorite IDE or some other tool just to validate your code if you want to. So. Correct. Exactly. One of the things we didn't discuss was the semantic analysis portion. There's some things that even your parser can't catch. And that would be things like, oh, you used a variable before it was defined. Semantic analysis, so your parser is, there's the concept of a context-free grammar. Context-free grammar means is we're only looking at this little thing right here, and if it's okay, we're good. Your non-context-free grammar analysis is your semantic analysis, where you go, oh, hey, I'm looking at variable y as being referenced here. Well, is variable y, is that a valid variable? you might have to go up multiple levels in the blockchain to find where variable y is defined and see whether it even exists, right? That requires a larger contextual analysis, and that's where your semantic chain comes in. So you have syntax errors, and then you have even further errors down the line that compilers will spit out. And then in our compiler class in a whole semester, we didn't even get into like optimizations at all. They have a whole, C compilers in particular are known for like doing things like loop unrolling and that sort of thing, where you're trying to get rid of every tiny possible double operation that's being performed in the machine code as final output. This stuff is really fascinating. It's a lot of fun to look into. Any other questions? All right. Well, thank you very much. I think it was a lot of fun. Hope you guys enjoyed it and hope you learned something. And maybe I'll come back sometime and talk a little more about some other data structure related stuff. I think that was the other topic we were thinking about doing. So thank you.